Hello folks, this is the first of the several video segments that I'm doing on analysis of composites using the finite element uh, solver that's integrated in CATIA, or I will refer to it as the native solver. Uh, these three problems have some similarities. For example, the first one that I'm going to be doing is a composite part like that, which is basically a single ply, only one ply, okay, 30 degree ply with respect to the global XYZ axis. And uh, after this composite part is being stretched along, or is being loaded along the X direction as shown here, okay. The total thickness of the laminate is 0.1 inch, and because we are using a single ply, that one ply itself is 0.1 inch, okay. Now uh, the the if I'm using a single ply as I'm planning to do it in this tutorial, this laminate is neither symmetric nor balanced. And what that means is that uh, when I apply a load like that, as you can see, this not only stretches, but it also deforms in the plane, in the shear mode. It shears in the XY plane. Furthermore, uh, mm, yeah, so uh, incidentally, this particular problem, the uh, you will see that we're going to be running two situations where in one case it's going to only stretch in the XY plane and shears, and the second one is going to be when it bends. We'll get to those later on, okay? Now, let me see now, the properties of this ply, the in the fiber direction and the transverse direction, the moduli are given here. These are all in PSI, okay? And the Poisson ratio is 0.25. In plane Poisson ratio is 0.25. Shear modulus is given there too. Now, what you see in the last column are the strength values in tension and compression along the fiber in the transverse direction and due to shear. This minus gave me a lot of headache when I was trying to do that in CATIA, and you'll see what I mean later on. Now, let me just say a few words about this particular problem. Notice that what happens is that if you assume that the load is applied in the fashion that you see in the middle, there will be no bending. There will be no bending of the part. Okay, it only stretches and shears. Okay, as you'll see. But if you assume that the laminate is loaded at the bottom edge like that, then of course it's going to go out of plane also. Okay, we'll get to that later on. Now we go to the last slide here. One of the objectives of this problem is to find for this one single ply that we have, find the stresses in the fiber direction and in the transverse direction, uh, and the shear, of course. And based on that, use a Saibu or Hoffman or maximum stress criteria to see whether the part will fail or not, the laminate will fail or not. Okay, now I mentioned that there are three tutorials. This is the first one. The next one that I'm going to do, I will repeat exactly the same problem, except that I will use two plies. However, because it's two plies, the thickness of each ply will be 0.05 if the total laminate thickness is 0.1. And finally, in the third example, I'm going to be using four plies. However, the angles in these plies are different. Even the second one that I'm going to be doing, they still have their two plies, but they're still at plus 30 degrees. So to convince you that if you have two plies of the same thickness, same material, same orientation, then there's no reason to think about it as two ply. You can do it as a single ply. Okay. So the final comment that I wanted to make here is that this video was done on Catia V56 release. Oops, this should be 2016. 2016. However, you can apply. You can do the same problem with other versions, higher or lower, except that some uh, icons and dialog boxes may be slightly different. But if you can do it in 2016, then with minor changes, it's not really changes, it's just be careful what you're doing. You can do it in other releases. Okay, so let's go ahead and right there. The first thing you have to realize is that this material that I'm using is properties of rough properties of carbon epoxy. However, you don't find that in the material database that comes with Catia. So the first thing that you need to do is to create that material. Okay, so we start with Catia. If you have never done it before, you start with Catia. You go to Start, Infrastructure, and under Infrastructure, you go to Material Library. Okay, notice that it's going to give you the option of creating a material. First of all, let me change this thing, right click properties. I'm going to call this thing, how about one ply, 30 degrees, okay? So first of all, uh, the name is one ply plus 30, okay. Now, apply, so notice that the name here changes, okay? Then you go to composite. The thickness, the cured thickness is the thickness that we do FEA on it is 0.1. Remember, it's going to be a single ply, total laminate thickness of 0.1, therefore cured thickness is 0.1. Now, I'll make it unidirectional, okay? And then the values, you click on the analysis, go to orthotopic 2D, and you start typing in the number that I've given you. So 20 e to the 6, that is the modulus in the fiber direction 1. This is the transverse direction, so it's 1.2 e to the 6. That's direction 2. Poisson ratio is 0.25. 0.25. Shear modulus, we were told that it is 0.8, 0.8 e to the 6. Now, these two are not going to be used, but we're going to put it in. So I'm going to put half of that value, 0.4 e to the 6. I really should not say they're not used, but I did not provide the values for you. 0.4 e to the 6. Okay, good. And now the strength value are down here. So longitudinal tensile is 300,000 psi. Okay. Longitudinal compressive is 150. Now you have to be careful here because in a lot of the literature, a lot of the information that you come in the literature, these values, for example, the compressive stresses, you put a minus sign in it. But when you put a minus sign here, CATIA detects an error and it will not run, but it will not tell you what the error is. So I spent a lot of time, a lot of hours trying to figure out what's going on. Why is it that it's not running? It's just because of the minus sign that should not be there here. Now in the tensile, in the transverse direction, it's 70,000 psi, and once again for the compressive, don't put negative. You put 25000. That's given to you. The table that I gave you has those negative numbers in it, but don't put it in there, please. And finally, the last line is 14,000 for the shear strength. Okay, apply, and we say okay. Now, uh, if you want, you can change the name of this change this thing to something else. It says new family here. You can change it to something else. But let me actually do that. Yeah, let me change this. So let me see now. Right here, I think this is the name. Rename family, and I'll call it my carbon epoxy. How about that? My carbon epoxy. You can add other members of the family, other families, and then what happens is that you can put them in different places in the tab. Okay. Now let's save this thing. So a file, save as, desktop, desktop. I'm going to give it a name. Say my own material or composite library. Composite library. Okay, very good. And let's put it in this. Well, actually, yeah, I'll put it I'll put it outside on the desktop. How about that? And I'm going to close it. And if you go to your desktop, because I put that thing in my desktop, it appears right there. I could have put it other places, but now from now on, the next three examples, I will add more stuff to this. I will not do all the steps, so I'll just add more stuff in that family. Okay, this is good. So let's go ahead. Let's start with the part, and I'm going to call it one ply plus 30. Okay, plus 30. Okay, so I have to create that surface there. So we're going to go to generative shape design. And it's a very simple surface. You could have done it in the wireframe and surface design also, but that's fine. So on that horizontal plane, I'm going to sketch a rectangle with dimensions 4 by 1, 4" by 1". So this is going to be 4". This is going to be 1". Exit. And I'm going to put a surface through that, and this is done with fill option, fill, and I say OK. Notice that this surface I could have created with drawing a single line and extruding. Same effect, doesn't matter. And I'm going to join this thing. There's a reason I'm going to join it, and I'll talk about it in a minute. Okay, now, this is joined now. Notice that in the tree, there's a join branch. If I double click on the join, the surface shows up, and it shows you a red arrow up. Now, when you join surfaces, you basically assign positive side and negative side. Positive side is in the direction of the arrow, negative side in the other direction. Now, when it comes to shell elements are, think about it as triangles or squares, stuff like that, or rectangles in 2D. So in the plane of the shell, there is local direction 1 and local direction 2. The third direction, which is the perpendicular to the 1 and 2, is always in the opposite direction of the joint in Catia, okay? I wish it was the same direction, but it's not. So if I flip this, okay, if I flip this, let me see, the arrow is pointing down now. And when I mesh this thing later on with shell elements, direction 1 and 2, of course, is in the plane of the surface, and direction 3 is perpendicular and opposite, which means in this case it's going to be in the upward direction. Okay, good. We're done here. Why don't we save this thing? File, save management, save as. In the folder here, one ply plus 30 degrees. Okay, now we're going to go to the Catia's composite design workbench. Catia design, composite design. Okay. The first thing that you need to do, is to create the parameters here, composite parameter. You click on it. There's no material here, so you're going to add a material. And I have to go to that folder that I created and retrieve that material. So I'm going to go there, desktop. This is the one that I created, right? You select it, say OK, and you say OK, and it's right here. This is the one that I created. Okay. Now, you may want to add other materials here if you want. You don't have to use it in the present problem. This is crazy. Why would I add other material when there's a single lamina made of one type of material? But adding it is not going to do you any harm. For example, I can even go to the CATIA. I don't have to do that. I can go to the CATIA's composite database right there, and all of these are already built in CATIA. I can take any one of them. For example, here, say OK, right there. But I'm not going to be using it. Okay, well, why not? I'll just leave it here. Okay. When you go, then you go to direction. These are the default direction, minus 30 degrees. So I have to add. So you give it a name, my 30 degrees. How about that? My my orientation. My, my orientation. I'll call it my 30 degrees. How about that? My 30 degrees. Now you put the value in here, 30 or plus 30, and the color, I'm going to change it so that I can recognize. Say OK. So there are these other angles too, but I'm not going to be using it. I just using the 30 degree angle there. Same with, for the same reason, there are two materials here, but I just want the first one. Now, we need to create a rosette, and that's one thing that I forgot to do. So that's okay. I'm going to say OK, and you can always go back to it. Notice that the rosette is not set. So what I have access right there. See that? I have access to creating a coordinate system. Okay, I could have done this thing in the generative shape design, or if I was in part design, I could have done it there. But because this is used very often, it's also put here for you in the composite design. You click on it. As soon as you click on it, it automatically places an XYZ aligned with the global XYZ at the origin of the part. But I don't like it to be there because I want this thing to be a little bit further away so that it doesn't get bungled up with this. So I put the cursor on this origin. See that? Put the cursor there. Right click, create a point, and the coordinates, I'm going to set y equal to minus 1. Okay, so that this will move there, as you can see right there. Now, this one is aligned with the global XYZ, which is great, but I can also use it as my rosette. If you want, you can create another one for your rosette, but that's okay. I'll leave it like this, okay? By the way, I'm going to uncheck this. I'm going to uncheck this. It says current. I'm going to uncheck this. Notice that the solid coordinate lines become dashed line, which means that that's not active. Now, I want to name this thing, okay? So I'm going to name this thing, right click, properties. Instead of axis system 1, I'm going to say align with big X, big Y, big Z. This is the global one. And I parentheses, I'll remind you that this is going to be also my rosette. Okay. So, all right. Now I'm going to create another one which is just like that, except that it's rotated by 30 degrees about the z-axis. So I'm going to create another origin. Okay, now when I remember, I made this thing not current because the coordinates, the measurement is made from the global origin. Otherwise, it would have, it would have done it from this point, which I don't like. Okay, so I keep the same y, but for x I increase it. This is good. Very good. And notice that it is aligned with the XYZ, but I want to rotate this thing by 30 degrees about the Z axis. So you put the cursor there, you put the cursor on Z axis, right click, rotation, and make this thing 30 degrees. Why I need this is because later on I want to plot the I want to plot um, the the stresses in the fiber and the transfers to the fiber with respect to this particular coordinate system, because the fiber runs along a 30-degree angle. Okay, it will be running along a 30-degree angle with respect to the global one. So the coordinate system appropriate for displaying uh, the, the contours of the, for example, fiber stress and transverse is this, not the original one. Okay, very good. I'm going to call this thing right-click, properties, rotated about Z by plus 30 degrees. Again, I want to remind you, if you don't want to plot those contours, but we want to because we want to compare our results with the hand calculation that you saw in that slide, the original slide, and in order to do that, I have to plot it in the correct coordinate system. Okay. Very good. This is done. So I'm going to go back to my composite parameters right there. Remember, I close this thing, double click on it. Remember this, the material that I want, something that I loaded, and I'm not going to be using it. This top one is from my own library. This bottom one is from the library. And then we define a 30-degree direction. We're not going to be using these because our plies, we can have more, but, and then we're going to have rosette. We're going to select it, add a rosette, and make sure you select this one that's global, in the global direction. Okay. Now, since I think release 21, there may be some changes in the way the rosettes are displayed. It looks something gigantic like that, which shows you the different directions. You know, 0, 90, 45, etc. Minus 45. But I also added 30. This is the one that I want. This is a 31. But I'm going to hide this. I don't need it. Okay, very good. That looks scary. Okay, good, good, good. So we say okay. There, this is my rosette. We say okay, and we save. Notice that if you look at your material, there are two of them, but we're never going to be using this in the present problem. Okay, so I haven't defined the plies yet. Orientation, there's several of them, including this last one. This is the only one that I need, but I decided to keep these, in case you want to change it on the fly. Okay, all right. So let's keep these things. Now, right, we're done here. So we're going to go to analysis and simulation, advanced machine tools. Now, if you're happy with triangular mesh, I think Katia calls it octree triangle mesh, something like that, then you don't have to go there. You can go to generative structure analysis and mesh it with that. But I want to use a nice fancy mesh, which is square in nature or rectangular in nature. So I go to advanced meshing tool. Okay, I will say okay. There is a surface mesher. This is the surface mesher. The one that's in the generative structure analysis octave triangle mesher is this. But I don't want to use this because, and there's an advanced version of the surface mesher, but I use the basic one. You click on this, you click on the surface. This red arrow tells you that where the direction of the normal of the shell element is going to be. And it points up because it's opposite to the join. Join, I flipped it so that it's downward. And the size 0.125, this is a good size, and quad only quad elements. So we say okay. Now you have to mesh it. This is what I call zap it or mesh it, mesh the part, and say okay, and exit. There's the exit, eject from that surface mesh, and there we are. Now, if I hide my part, you will be able to see the mesh. Change the rendering here to the one with the edges. You can see right there. Okay, good. We don't need this. Now well, not that we don't need it. Now we have to go to analysis and simulation, generative structure analysis, because that is where you apply restraints and loads and stuff like that. Now, uh, okay, first let me, by the way, if you can see the mesh, right-click mesh visualization, you can see that right there. Incidentally, just to convince you that my normal to the Z, normal to the uh, plane, normal to the uh, element coordinate system points up, I can put the cursor there on that line, right-click, generate image, and select the local axis symbol, and say OK. If you zoom in, you see what happened. These are the centers of each one of those rectangular or square, in this case, meshes. There is 1 and 2. This has nothing to do with the orientation fiber and fiber and the transverse orient. This is the local coordinate system for the element, shell element, is in the plane, and 3 is up. Okay. Now we don't want this, so I'm just going to hide it or delete it. It's up to you. Right click, deactivate it. Okay, very good. Now, just be careful. The load that you have to put on this sheet is going to be on these edges. But right now, there's quite a few things that are obscuring that edge. One of them is actually that rectangle that initially I drew, the sketch. And then there are those. There's that ply that I. Oh, you know what? Oh my God! I forgot to create my ply. Oh boy, let's go back. I forgot to create my ply. Let's go back to, I went there too soon. Okay, but that's okay. We can fix it. So we go here, go back to your composite design. I forgot a big step here. Wow. Okay, so we are in composite design right there. Uh, this stuff is for the finite element. Don't worry, we will go there later on. Now, we have to create a ply group. The method that we're using is called manual ply creation, which is very tedious if your problem is complicated and you have a lot of plies and things like that. But in our case, there's a single ply. Really, there's nothing to it. So it says, okay, what is the surface? There is a surface. I'm really sorry. I should have done this thing uh, before I go into finite element module, but it's okay. We can always fix it. We did it. Now, the draping direction is the direction along which the plies are going to be stacked on top of each other. Okay, so I'm going to flip this so that the, the direction is along the z-axis. Remember, this is the third axis of the element. Okay, now the rosette 1. And when you say lock plies draping direction, in other words, make it in this direction, okay? Because it is possible for the draping direction in the plies group to be different from individual plies, but I don't know why we would do that. This is crazy. So that's okay. All right, so we created a plies group. Now we're going to create a ply right there. See that? This was plies group. See, the name of the toolbar is plies. This was plies group. This was ply. You click on the ply. If you look at the bottom left of the screen, it says select the group or sequence or apply to paste the ply, to create the ply. So this is the group that I created. So it's asking you to select this. You can't select anything else. Okay. Select this. And then it says, okay, what is the boundary of this ply? Now, it's obvious for this particular one, this particular problem, that sketch is a perfectly good choice. So either I take it from the screen here, or I can go to the tree right there, and notice that it selects it, so the ply is going to look like that. Now the attributes. Remember, uh, the material, this is the thing that I created. Remember, I created 1 ply plus 30 degrees. I created that. It is possible to select the one that came from Catia database, but I don't want to do that because those are different other things, other materials. Direction, we have all of these choices. This is the one that we want. we say 30 degrees. And rosette by default is going to be the same as the group. Okay, so perfect. We created our group, our ply. Where is the ply? Right there. Right there is the ply. This is a sequence. This is the ply. If you double click on it, it shows you the ply upward. The attributes is exactly what I wanted, and we say OK. Now, you can also show this thing schematically. There is a ply exploder here. There's a toolbar which is called analysis. There is something here called ply exploder. You select it. There's a ply group, and you say apply, and it shows you the one ply that you create. This is the original reference surface. The mesh is going to be on this surface, and then the ply for visual purposes is shown to you in this way. Okay, and cancel that. Well, I'll say OK. But my point is that once you do this, then you better either delete it or deactivate it. So you put it on the stacking engineering, go down, and either delete it, exploded surface, or there's no there's also deactivate somewhere. I'll delete it. Okay, good. Now go back to generative structure. Remember, we went there, we created the mesh, and then we realized you forgot to create the ply. So go back to generative structure analysis. So you can double click on this. Puts you in generative structure analysis. This is where we're sitting, but we left. Now, right, we're going to apply our load on these edges. So the way I'm going to apply the load is consistent with the way the literature works in uh, composites. So I'm going to apply it as a line force density, another force per unit length. You click on this. Let me change this thing to 0. This is what you get initially. Okay. Now I want to say on this edge, it is 1,000 pound force per inch. I could not change the unit so that it would show pound force per inch, but you can always type 1,000 lbf underscore in. Now be careful for the support. You can't select these because this is actually the Plies probably. So let me hide my stacking sequence. You put the cursor there, right click hide, and this one is the sketch probably. So hide the sketch, put the cursor there, right click hide, and now the edges will appear that you can actually pick. Okay, there. So you select it. If you zoom in, you see that it's in the right direction, and it converted it to Newton per meter. That's what it was originally. I changed it to 0 so that you don't say, well, where is this coming from? Comes from here. All right. And then on this side, again, what is that? Same thing. On this side, except that this number should be negative. And we say OK. Notice that if you look closely, it's being pushed in the right direction. Okay, now if I run this thing, first of all, not run. I mean, obviously, I don't even have materials specified on it. Okay, I have, because I created the plies here, but this guy doesn't know. You know what I should do? Maybe I should apply the material right now, or not apply. Ordinarily, once you use shell elements, you need to use 2D property. Now, under normal circumstances, 2D property is the thickness of the shell, but if you expand this thing, you see that there's another thing which is called imported composite property. Don't use this. This is not for composite. You have to use this. And you click on it. So now it's going to go there and start using these direction and the material properties and these things that you put up there. First of all, you can do it by ply or by zone. I'm not doing zone yet. I'll do it zone in different video segment. Okay, this is the most elementary way of doing it. So support is actually the surface, and by ply, and you click on that wrench, and you go and select your ply or ply group. Okay, ply group right there, ply group. ply group, or you can select the ply. Okay, so let's say ply group, and we say okay. Now this box which is symmetrical. Remember I showed you in the original video, original slides that I put up there. Whether you check this thing or not, the problem will assume, if you check it, it assumes that this ply is placed so that it's symmetrically above and below this reference plane. In other words, 0.05 inches up, 0.05 inches down, so the ply sits there. If you do not check this thing, it assumes that the entire 0.1 thickness of the ply is above that, and this is why it's going to be bending. I will do it with bending for you later on. Okay, I'll just remove that and show you how it works. Now, so material is set right there. You can see that right there, right there. Notice that there's nothing in here in the material. If you want to access this, material, there is a way to do that. Let me quickly show you. So you go to File, Desk, and this is, remember I used my own material database, catalog, and Catia's catalog that we picked something out of, we're not going to be using it. But if you select my own, right click and you say Open, it goes there and you can double click on it, you can make changes to it, etc. So I'm not going to do that. So I'm going to close that, and I'm going to close this thing. You're back here. Now, if I run this thing, it's going to bomb out because this part is free to move as a rigid body. Okay. Now to fix that, I can use the so-called 1-2-3 rule. For example, I assume that one point does not move in X, Y, Z direction, which means that this part can now be just pivot around that. Another point cannot move in the Z direction and the X direction, which means that it can shrink in the Y direction. Now, if I do that, then this thing can hinge about that line. To avoid that, we one last point to prevent moving up. And this is why it's called the 1-2-3 rule. There are easier ways of doing this thing in CATIA using the isostatic restraint, and there are some videos that were done for it, but not for composites. You have to go and look it up. It's something that can be dangerous. This is why I'd rather do it this way. So, so remember this. I said that corner point. We zoom in. This corner point does not move in X, Y, Z. Really, it's clamped. That's what it means. That corner point does not move in the direction X and Z. It can move in the direction Y because this thing can do 2-Poisson ratio, can actually shrink in this direction. And the third one, any corner point, for example, this guy does not move in the Z direction. Now, why don't we go and save our analysis? So, where is this file? Save management. The analysis right here. Save as. In desktop, I made it this folder. Okay, analysis 1 is fine. I can give it a different name if you want, but that's okay. And we say okay. All right. So now we're gonna run it. And I always pray when I say compute, because things I may have forgotten stuff. Oh, yeah, I may have forgotten stuff. Oh, it did run. Okay, right there. All right, let's look at the deformation first of all. Displacement. Aha. Let me change the rendering here to material shading. Average ISO, material shading. And if you look at this thing from the top, you can see that it not only stretches, but it also shears. You can already see that because at that 30-degree angle, you can animate it right there. Right, okay, very good. So let's put this thing in the, right Now, to convince you, we're going to come back and look at the the stresses here. That's really to convince you that something is going to go wrong. If I go to that imported properties and I uncheck that and I say okay and then run it, it will run, but you will see there will be bending out of plane. Okay, so let's go and plot the deformation and change the scale here. Change the scale here. Don't let this thing scare you. Go there and say default. There. You can see that it not only stretches, but it also comes out of blue. This is not what we want. This is not what we want. Okay, so let me go ahead and change this thing back to symmetrical. I've got to run it again because I want to show you the split, the stresses here. All right, very good. Now, suppose you want to see what the stresses are in the in the ply. There's only one ply here, but later on we're going to be ply 1, ply 2, ply 3, etc. So I want to see what are the stresses in the global direction. So if you put the cursor, remember, doing it globally like this, it won't let, actually it won't let you plot the one meter stress here. You have to do it the way I'm showing you. You put the cursor here on the static case solution, right click, generate image. There's a lot of stuff that you can plot, so I'm going to filter it by stress. So these are the things that you can plot in the stress and nodal component. Now, this is why I created 2 video segments about tips on plotting stresses in shell elements as a part of the FEA playlist. You won't find it in this playlist, okay? So you may want to go there if you want to see what's going on. So we say, okay, so there we are. First of all, what the heck is it that I'm plotting here? Let me double click on this again. Oops, just a second. Okay, my mouse is on a battery, just be patient. Let me try another mouse here. I've spent enough time on this so that do another one. So let me see. Okay, good. Now, let me double click on this again and see what is it that we are actually plotting here. So if you say more, it says this is the stress plotted in the local coordinate system of the shell. Totally useless, okay, for me. So I can click on this and say, okay, I don't want the local coordinates of the shell elements. Give it to me as the global one. Ah, this is good. So this is C11. Remember, you can plot C11, C22. This is C11, C22, C33 in the direction. C11 is basically sigma x, sigma y, tau xy. And don't let this thing scare you. They're all the same number, 10,000. And where the 10,000 comes from, because it was 1,000 pound force per inch divided by the thickness of the lamina, that's going to give you 10,000. If I go to C22, I did not apply any force in the y direction. You're going to get all zeros, 0, 0, 0. And if you go to shear, also all zeros. The only force that I applied was in the x direction. And this. Now, suppose we want to plot the stresses in that rotated coordinate system. So we're going to say, okay, I don't want global. I want user, okay? User. And user, you either go up here and select the right one, right there, right one, rotate by 30, or you say, okay, show me all the coordinate system. You put the cursor there. You put the cursor on the part, right click, hide and show. I don't want actually the join here, hide this, but the coordinate system is appearing there. So you pick the coordinate system that you want and display the stresses in it. So select this. I selected it. That's the coordinate system rotated by plus, and you say OK. Now comes the moment of the truth. C11. Let me go get that PowerPoint. Remember, 7. This is this is the stress in the fiber direction. 7,500. Let me see. 7,500. We're apply plus 30-degree ply. The last one, and 2,500 and minus 4,430. So let's go ahead and check it out. What is this? Okay. C22. There is your 2,500. Shear minus 4,430. There. Now, there's a single ply here, so it shows you only one. But if you have multiplies, then you can march through the plies and one by one get these things. You'll see that in the next video, next two video segment. There's something else that I want to do, and that is in the event that you want to plot the von Mises stress here, for example, you can do that, von Mises, and don't let it bother you. It's going to be also 10,000 because two stresses are zero. This is in the ply. Two stresses are zero in the y direction and shear, and sigma x is the only dominant one, which is 10,000. But I want to show you something else now. Let me see now. So we say fine. Now, if you go and put the cursor on the place that allowed you to plot the these things. So let me deactivate that first. Okay. So you put the cursor on static case solution, right click, once again, generate image, and then I'm going to say filter it according to the failure criteria. Sahil, right? Saibu is what we're going to do. We're going to do these three. You say okay. There we are, 0.262. The Saibu, if this is less than 1, it's safe. Bigger than 1, the ply will fail. Now, let's see now. Saibu, Catia predicts 0.262. I've got a problem here. Just a second. I'm sorry. 0.262. Okay, so that's fine. What's the other one? Let's do another one. Failure criteria. Hoffman, 0.269, and maximum stress. Deactivate this, and this one is failure .357. Now just notice something, and that is, you see, this one is correct, this one is correct. These two, with hand calculation, I'm getting different numbers because I don't think these are correct for the thickness that I used. I don't want to spend more time on this right now. There is this one is correct, and this one there is some issue with it, and it has something to do with that. When I did the copy and paste for these three video segment, I I I I used probably something else for this. So wait till the second video segment. We're gonna get identical result to what you see here. Okay, so this is not wrong. It is just that these numbers for Sahil and Saibu based on hand calculation, these are not correct for the present problem, okay? So that will do it. This is why, on purpose, these first three video segments, they're kind of repeating the stuff uh, several times so that you get the hang of it. So everything worked out except that my Saiwu and Hoffman did not give me the numbers that I showed you here. But that's because this was, I'm sure, inadvertently copied from a different video segment. Okay. If I had my MathCAD calculation, I could have done it for you and showed you. As a matter of fact, let me see for a second. Let me see for a second. I have my MathCAD calculation in my other computer. Just bear with me for a second. Uh, one ply, right? One ply. Yeah, we're gonna get there. The second one, we're gonna fix this thing. Sorry about this mishap at the end. Good luck.